Aaron said, we're going to be talking about the sun and climate. And sounds like a popular topic based on the number of people I see in here, and that's pleasing because it's one that I've kind of gotten fascinated with as well. I've been studying the sun for a while, and I used to have an advisor who was a theoretical cosmologist, and that may sound redundant, but in this case it really wasn't. So decided I wanted to work on something that was a little bit closer to home, something that we could actually go drop an instrument into if we really wanted to. I didn't quite appreciate at the time that the sun is the hardest thing in the solar system to hit, energy-wise. And the reason is our Earth out here is spinning around the sun at about 18 miles a second. So to really get into drop something into the sun, you've got to counteract that with 18 miles a second of rocket to be able to fall straight into the sun. If you don't do that, you're going to kind of whip around the sun real quickly, and you're not going to hit it. If you do 18 miles a second forward, you've got more than the velocity you need. You need about 12 kilometers a second is all to get out of the solar system. So it makes the sun the hardest thing in the solar system to hit. So I've given up on the idea of trying to get anything there and settled for simply observing it remotely, which is a whole bunch safer anyway. But here's the sun. And for climate, what we're interested in is just the outer surface of this. Outer surface is 5,800 degrees Kelvin, so a little less than 10,000 degrees Fahrenheit. And it's 100 times the diameter of the Earth, makes it about 1 million times in volume bigger than the Earth is. And it's at a distance of 93 million miles from us. The way it interacts energetically with the Earth is purely via photons. So basically all the energy from the sun that's heating the Earth is coming radiatively through photons. Most of them are in the visible, and a fair number also here in the infrared. It does put out energy all across this spectral region, but most of the real energy is in the infrared and the visible here. And it takes those photons at 93 million miles, a whopping 8 minutes to get to the Earth. Now, I'll mention in a while that those photons came from reactions that happened a long, long time before that 8 minutes. So when those photons hit the Earth and heat it up, some of them are reflected straight off of the Earth. Some of them really do go into heating up the Earth, and then they can be re-radiated in the thermal infrared. And it's kind of a balance of this incoming energy and the outgoing thermal emission minus the reflected portion that we've kind of lost, reflections off of clouds or the surface, that determine the Earth's temperature and give it at about 2,800 degrees Kelvin or 45 degrees Fahrenheit. And that's kind of what gives us basically our climate. Where does the Earth really get its energy? Primarily it's from the sun, solar irradiance. Irradiance is kind of the whole sun, spatially integrated, spectrally integrated, all the radiant energy that's coming from the sun. So that gives us a worldwide average of 340 watts per square meter, but I'm simply going to call that 1 here. I've normalized everything to the sun. So all the other energy sources, all that we could really think of, are kind of listed here. The next most dominant are heat flux from the Earth's interior from radioactive decay and geothermal activity. And they're down a factor of 4,000 from what you get from the sun. There are things like combusting various types of organics that we have, infrared radiation from the full moon, solar light that's reflected off of the moon. You can go right on down here, because these get to be more and more absurd. Tidal forces, magnetic storms, lightning, micrometeorites coming in, radiation from stars. These are all, you can add them all up, and the total of all of them together is still 2,500 times less energy than we have coming in from the sun. If you've done much with climate, you've no doubt heard about greenhouse gases, and you'll notice that they're not on this list. They're not in here at all. And the reason is they're not an energy source. They affect what happens to this energy as it comes in and as it tries to leave, but they're not an energy source. What's really driving the climate is the sun. That's where we're essentially getting all of our energy. What does that mean? I add all of this up, and like I showed you a couple of slides ago, that gives us a temperature of about 45 degrees. Now, the Earth globally is a little bit warmer than that. That's because the greenhouse gases do kind of hold and trap some of this energy in the sun. But what would happen if we didn't have the sun? Well, we wouldn't be getting infrared radiation from the full moon. Well, the big one is, of course, we wouldn't have this whopping huge effect on top of the moon. We wouldn't have reflected energy from the moon. We wouldn't have tidal forces. We wouldn't have magnetic storm energy. We wouldn't have a few of these other kind of insignificant energy items. But the big one is losing the sun. We'd be down at almost minus 400 degrees. And actually, if we didn't have the sun, we probably wouldn't be combusting a whole bunch either. So that cools us another couple of degrees there. So basically, without the sun, we might still have something you could call climate, but you wouldn't be very pleased with it. So that's why the sun really is the big driver of climate. It's the dominant driver of climate. And luckily for us, it's fairly stable. It is dominating everything else in this energy budget, but it's a pretty quiet, mellow, for the most part, sun in terms of climate drivers. Here's how we really overall try to determine climate. We have total solar radiance, all the spectral, all the spatial information from the sun is coming in, providing, like I've said, all of the heating that the climate system needs. That energy comes in, about half of it comes straight down here to the surface and gets absorbed. A third of it gets reflected off the surface or reflected off the clouds as it tries to come in. A little bit gets absorbed by the atmosphere on the way in. These reflected photons are still basically solar, that is, they're visible and they're infrared. The portion that gets down here to the surface goes into heating things up, and then the Earth radiates away in the infrared. A little bit of that manages to squeak its way out through the atmosphere, but most of it gets absorbed by greenhouse gases that are up here in the atmosphere, and then they re-radiate at a different temperature, and a lot of that comes right back to the Earth, and some does go on out. But this is an overall picture of what the climate is like. Now, a lot of these processes are really complicated. So, and you'll appreciate also how the total solar radiance is kind of complicated, but after that, things really get complicated when you start dealing with all of the interactions that you can have down here in the atmosphere and the Earth. So we're going to study something that's relatively simple, the incoming solar radiation and how that interacts with climate. So let's talk about that sun's energy. The energy coming into the Earth is 1,361 watts per square meter, so roughly a little space heater in every little block, every chair you're sitting on, roughly. Space heater roughly putting in energy to one whole side of the Earth all the time. The total output from the sun is 4 times 10 to the 23 kilowatts. Now, that's a whopping huge number, and nobody in this room can comprehend how big that number is. That's enough energy that the total output from the sun in 1 second would supply the Earth with energy for 9 billion years. So that gives you a little bit of perspective for how much energy is coming out from the sun. It's also a neat little bit of more unfathomable trivia. The sun produces all this energy right in its core, and that energy, the sun is under so much pressure there that the densities are 150 grams cubic centimeter. It's about 12 times the density of lead. And remember, this is hydrogen. It's really light stuff normally, but it's compressed to be about 12 times the density of lead in the core. So the density is so great in the inner part of the sun, and the sizes are so big that those photons don't go very far before they get scattered, absorbed, re-radiated. It takes them somewhere between 150,000 years and 1 million years to make their way to the surface. So that 8 minutes that I mentioned a couple of slides ago really is nothing compared to the time that those photons have been bouncing around anyway. Some neat little trivia about the sun, how energetic it is, how big it is, how dense it can be. Solar atmosphere for climate, even though there's a lot of neat structure on the surface of the sun, for climate, we really mostly care about that 5,800 degrees, because that's a lot of what's determining the temperatures of the Earth. Now, you've probably heard about some of the differences between climate and weather. Weather is climate is sort of the long-term average of weather. Another way of putting it is climate is what you expect to get, weather is what you're stuck with today. So, same thing with the sun. There are coronal mass ejections, there are flares, there's a lot of short-term activity on the sun that can impact the Earth. And some of these are impressive as well. Coronal mass ejections will spew off tens of billions of tons of material. And here's a huge bit CME, or coronal mass ejection, being thrown out from the sun. And here's the Earth for comparison of the size of the laser pointer spot up there. That stuff gets thrown out about 1 million miles an hour. And these can have short-term influences on the Earth. Here is, over about the course of 12 hours, a large coronal mass ejection coming out, and the sun itself, the disk, is that size right there. So that's lots of particles, and huge amounts of matter getting thrown out at 1 million miles an hour into our solar system. And that can have some effects when it hits the Earth. Some of those particles can ionize our upper atmosphere and can change the height the atmosphere goes to, and that can have an impact on spacecraft that are up there, it can impact communications. This is a profile of the height of the International Space Station, which is normally up around 400 kilometers above the surface of the Earth. And as it orbits up there, it's got a little bit of drag from the atmosphere that it's running into. So you can see that it drops and drops, and then we go up and we occasionally reboost it. And you see that as it drops, it starts to drop more steeply because it's getting into denser and denser atmosphere. So the rate that it's dropping increases the lower it gets, and we reboost it. Here was a case where there was a large flare in 2000, and that managed to drop the International Space Station about 15 kilometers, just almost overnight. You can start to imagine what would have happened if that had occurred, say, right about here, where it really would have been falling into the atmosphere a lot faster than where it happened to be when that one went off. Now, the sun goes through these 11-year solar cycles where it gets to be more active and less active. And you notice that solar maximum here, we know that the sun's going to be pretty active, and we're smart enough to keep the International Space Station up a fair amount higher than we do when we can get a little lackadaisical during solar minimum, let it get a little bit lower because we know the Earth's atmosphere isn't ionized, isn't as high as it can be during solar maximum. So these are direct effects, but like I say, these are kind of short-term effects. They're what you call space weather instead of climate. So let's go to the other extreme, the real long-term. How is the sun changing and how does it impact climate? This is kind of where the sun is in terms of brightness as a function of age. And right now the sun is middle age, getting towards middle age, perhaps 4.5 billion years into its 12 to 15 billion year lifetime. And as it's aging, as it's burning hydrogen into helium in this main part of its life cycle, it's gradually getting brighter. It'll eventually get to be, before it really goes a little berserk on us, it'll gradually get to be about 3 times as bright as it is now. And it used to be about 30% dimmer than it is now. So over time, it is going to be getting brighter, and that's going to be changing climate. This also isn't real interesting for climate because it's so far beyond our lifetimes, it's so far beyond the time ranges over which the entire Earth will have changed, continents drifted, bombardments happening, that it's also not real relevant for most climate studies. So let's pull ourselves back a little bit to a more reasonable time frame. There are orbital changes in eccentricity of the Earth moving around the sun, changes with about 100,000 year time scale. The axis tilt, which is a lot of what determines our seasons, changes with time with a 41,000 year period. combination of how that axis is oriented with where we are in the orbit changes with roughly a 20,000-year time cycle. These are the Milankovitch cycles, and here are each of those shown with their combined effects for the solar forcing that you would have compared to different stages of hot and cold for glacial periods that we've had going back about 1 million years. And you can see there's some classic cases where low solar forcing corresponds with colder temperatures, high solar forcing, high temperatures. Some of these line up pretty well, other ones a little bit less so. But this is something that is a direct, just because of orbital dynamics of the Earth, direct connection between what the sun, how the sun is driving our climate. So over reasonable time frames. But let me also give you an idea, even over a year or so. This is 2001. Various sunspots on the sun, just how dynamic it can be. You can see some large spots forming, and sun rotates with about a 27-day period. That's the time scale by which these are rotating around. But over this 1 year, over these several rotations, you can see a lot of changes in what the sun is doing. It's active on minutes, weeks, months, years, and we don't know so much about centuries, but we would really like to for climate studies. So, I'm going to talk about sunspots for a little bit, not because they're directly driving climate, but they're really good indicators that we use for a lot of what we know about the sun and how it does change over long time periods. So here's a picture of a sunspot. A sunspot is a cool, if you can call, say, 6,000 or 7,000 degrees Fahrenheit cool, cool region of the sun. And it's twice in diameter what the Earth is. Earth's shown here for size. Very strong magnetic fields, 4,000 Gauss. For comparison, the Earth's magnetic field that we measured here is about 1/2 of a Gauss. So very uniform, strong magnetic fields over center portions of these large sunspot regions. So their active regions are kind of indicative of activity on the sun. The reason they're neat is we've got 400-year record of what these sunspots are, starting regularly. The prior observations went way back, but we have regular observations from about the early 1600s, when several people started using telescopes to really be able to draw maps of what sunspots were regularly. Galileo being one of those who instigated what we now have as a wonderful 400-year sunspot record. Early on, people didn't really know what these were. Galileo himself said they were cloud-like structures, which kind of made sense. One of the ones I like most was William Herschel, who was a brilliant physicist, but this wasn't exemplary of some of his better work. He said they were openings in the sun's luminous atmosphere, letting us see the cooler underlying surface, which he presumed to be inhabited. Herschel also, although people didn't appreciate it as much at the time, correlated the price of wheat in London with sunspots, and attributed that to less rainfall at times when the sun had fewer spots on it. So this is the first really published record of a link between the sun and Earth climate somehow, and one we've gotten to appreciate a lot more than I think he or anyone else ever did earlier. Another example, the late 1600s. You study climate, you know that as Europe's Little Ice Age, time when winters were longer, harsher, rivers were frozen over longer than normal in Europe. Lots of drawings and paintings of festivals that they were able to have on frozen rivers that normally weren't frozen. If you study the sun, you know that it's the Maunder minimum, time when, like I said, we in 1610 started taking sunspot measurements, and sunspots shown here in red have this 11-year cycle that you see causing these spikes. Well, for about 70 years here, they largely died out, and in solar physics, that's known as the Maunder minimum, time when the sun was fairly inactive magnetically for that duration that corresponded with Europe's little ice age. Here's a picture of the total solar irradiance, the radiant output from the sun at the Earth. And you can see that with time, and this is about 3 months here, it can have some large variations. And I'll show you what that looks like here. As the sun's rotating around, and these spots are going across its disk, you can see short-term decreases in the sun's output and increases due to activity around those sunspots. But these are 0.1% or a little bit smaller, but still they're bigger, remember, than all the other energy sources combined that I talked about earlier by a factor of 10 or more. Now here comes a large sunspot onto the disk, and as it's leaving, another one comes on, and a third one forms. And that's a 0.3% decrease. That's the largest short-term decrease that we've seen during the spacecraft era in the sun's output. So it can do that over days to weeks. What we really want to know for climate, because these days to weeks are too short of a time period for the Earth's climate system to respond, what we really want to know is what's it doing long term. But given that it can vary this much on short time scales, we need to know how variable it can be on long time scales. Now let's start to wonder about how things correlate with the Earth. Here's 150-year record of temperatures, globally average temperatures of the Earth, and actually its temperature changes. It shows an increase in the last 150 years of a little less than 1 degree Celsius, so 1.5 degrees or so Fahrenheit, with most of it being in the last part of the 1900s. These maps here, maps of the Earth, North America here, show the difference in the bottom one between the mid part of the 1900s and the early part, with the colored temperature scale showing changes. And really this is saying that things didn't change a lot temperature-wise during the early half of the 1900s. Here's the latter half of the 1900s, with these red areas being a couple of degrees warmer than they were in the middle part of the 1900s. And mostly you'll see that affects Northern Europe, Northern Asia, and Northern America. So that's 150 years. Going back prior to that, the temperature record was pretty stable compared to what it was doing those last 150 years. There's a large spike here, but prior to that, things were much more stable. Now, most of this is due to anthropogenic effects, human-caused effects, things like greenhouse gases that we're burning. Prior, it was more driven by natural effects, things like the sun, volcanoes. So to really study solar influences, it'd be nice to have a good record back here when things weren't swamped by what was going on more recently with anthropogenic effects. So we'd like a long-term record, and luckily, like I showed, we have a 400-year record that's not directly irradiance from the sun, but it's an indirect indicator of what that irradiance is due to this sunspot record. So, some connections. I've shown this longer minimum period, 70 years, where the sun was a little bit dimmer and temperatures were a little cooler on the Earth. But there are other effects as well. There's this 11-year solar cycle, and that signature shows up in tree rings. So we can see in plant growth the effects of an 11-year solar cycle. That 11-year cycle is correlated with ozones, with winds, with clouds, precipitation, even with fires, with ocean atmosphere circulation patterns. So we've got a lot of correlations between that 11-year solar cycle and signatures on the Earth where we can see that 11-year solar cycle. So a lot of those are correlations, but sometimes understanding and especially predicting things can be a lot more difficult. But there are a lot of connections between the sun and climate. What do we really need to be able to determine climate sensitivities? Basically need two things. We need very accurate and stable long-term measurements of the climate and whatever we think is driving it to be able to compare the two. But that's not enough. We also need to understand the cause and the effects that things are having, some kind of physical rationale for why one would be related to the other. So here, for instance, is a record of changes in temperature in white. And then the model of those fitted to solar effects, shown in green here, and anthropogenic gases, which are increasing with time during this last 30 years, give us a model that roughly follows those temperatures. Those are things that are kind of rational. We'd understand why a warmer sun would heat things up, why greenhouse gases would be causing increases in temperature here. So we can say that we understand some of the cause and effect there, and we have some record, reasonably good record, that meet both of these criteria up here. And then we can attribute for a change of 1 watt per square meter, say in the sun's output, that we get a change on the Earth of 0.06 degrees Celsius or 0.1 degrees Fahrenheit. So I can make some sort of sensitivity, 0.1 degrees Fahrenheit per watt per square meter of change from the sun. So that's a case where we have a reasonably good record. We have some rationale, physical mechanism to say that one's related to the other. Here is our total solar radiance record. I've combined this a little bit, and I'll show you how in a few minutes. But I can take that record and correlate that with sunspots. Here we've got a peak of a couple hundred sunspots that are on the sun during these monthly averages. So you can see a correlation between irradiance and sunspot number. So like I said, sunspots aren't really driving the climate, but they're indicative of other effects on the sun that are driving the climate more. So I could make that relation and say now I've got 0.001 degrees Celsius per sunspot on the sun. And that might be a reasonable proxy for cases where we don't have direct measurements of the sun. We've got the sunspot record that's kind of a proxy, sort of an indicator of what the sun is doing. But let me give you a bad example now of correlations. Correlation does not imply causation. Here's a relation between sunspots and Republican senators. So you can, if you got too many records, you can find wonderful correlations at times when. So in this case, we definitely don't understand the cause and effect. Floating criteria number 2, and we actually don't have a good long-term record. Fitting 2 cycles, senators tend to come and go on a 6-year scale. And
boy, that's really tight.
Over that time period, that's really nice and tight.
Yeah.
Interesting to extrapolate either direction, but 10 sunspots per senator. So you have to be a little more careful than that. Climate quality measurements are difficult. Coming out of under minimum here, these are estimates of what the sun, how quickly the sun was changing coming out of under minimum. The sun didn't change a huge amount, but remember, it's putting in so much power it doesn't have to change a huge amount to affect climate. So these are different models for how quickly the sun was changing. I take the more extreme of those, and over the 80 years or so when the sun was coming out of under minimum, it increased by something on the order of 0.1%. So you want to be able to track a change of 0.1% over 80 years or so. And that's the real difference between a climate measurement and a weather measurement. If you have a thermometer, you can go outside and you can measure the temperature today, and you can see a big change that happens between today and tomorrow real easily. But if you want to see a change in these temperature changes I've been showing are tenths of a degree happening over 100 years. How accurate is your thermometer over 100 years? Does it change at all? Or you lost that one and now you've bought another one, and how well does it match with that first one you had? Or you give it to your brother to take over the record for some time, and does he really read it exactly the same way you do? So if you're doing climate studies, you need instruments and measurements that are incredibly stable and incredibly accurate over incredibly long time periods, and that's what makes them so much more difficult than doing kind of weather-oriented or short-term measurements. Climate requires long-term measurements with good accuracy and good stability. we started getting measurements of the sun back in the early 1800s. And they really aren't useful for us right now, but it was an attempt. 1838, Cuvier started to measure the sun, and he used this black surface container of water and measured the temperature change on the water. And he, of course, was restricted to the ground, and he was low by a factor of 2 from what we really know the current value to be now. And that's because, like I showed earlier, only about half of the incoming energy makes it straight down to the ground. So, but good first attempt. Here's what we have now. We've got a 32-year-long record from space given to us by about a dozen different instruments. And you immediately look at this and say, gee, they don't agree with each other. Now, I've expanded the scale here so that this range is 1%. Still not good enough, but what really has saved this record is there's overlap between each of these instruments and the next, so that you can take them all and shift them and put them together like this to have one composite record. So that's our total solar irradiance climate data record. Each of those instruments is real stable, even though the offsets between them can be rather large. What explains most of that variability? Here's our composite record. Most of it comes from 2 components on the sun. Now, I showed you sunspots, and maybe I should go back here briefly. Here's correlation between sunspot number at the bottom and total irradiance, shown right here. I showed you the movie earlier where when sunspots went across the sun, they caused a decrease, and they do. So sunspots themselves cause a decrease. But around those sunspots are these other magnetically active regions that are hotter, warmer, brighter, and extended over much bigger areas than the sunspots are, and they last much longer. So what explains most of the variability in the sun is a combination of these faculae, magnetically bright, active areas over big regions, and darker sunspots. So the darker sunspots do cause short-term decreases. This is not noise in the data. Each of these is the passage or formation of some sunspot region going across the disk. But overall, the faculae win. They make things brighter, despite the sunspots trying to make them a little bit darker at the same time. So these kind of opposing but linked forces give us what really is coming out as irradiance. So the faculae win, but we don't have a good 400-year record of faculae, unfortunately. We do have a good 400-year record of sunspots, and they are correlated pretty well, and we understand a lot of the physical mechanism behind how they're correlated. So we can use the sunspots as a good proxy, a good indicator of what the sun has been doing for the last 400 years. So if you want, like I said, you need a long-term record to do climate. We're not patient enough to sit around and keep measuring for hundreds and hundreds of years before we start trying to figure out what's going on with climate. We want to know right now. So the best way of getting that is to go back in time. So we take our 32-year record and we offset each of these to give ourselves one composite record. We correlate that with the sunspot record that we have over that 32 years. We then take that sunspot record and it goes back 400 years. So we've got a 400-year record of sunspots, which are indicative of total irradiance, not a direct measurement of it. And then we can say, okay, now we think we know what the irradiance was doing for the last 400 years, but maybe it wasn't really flat. Sunspots, you can't have negative numbers of sunspots. So this never really drops a bunch, but the solar activity might have changed a bit based on average of the sunspots or duration of these sunspot records. So various people have come up with different models that trying to understand the magnetic activity on the sun, of how the sun was lower in activity at times when it was lower in numbers of sunspots long term. So that gives us some reconstruction of what irradiances were over these last 400 years, but we still want to go back further than that. And one thing the sun does is we've got records on the Earth of cosmogenic isotopes. What these are cosmic rays that come sailing into the Earth's atmosphere and they create various isotopes. Beryllium-10 and carbon-14 are two of the most used ones. Those settle out from the upper atmosphere and either get absorbed by organic life forms, trees, where we can go through tree rings and measure carbon-14 and date the carbon-14 via the tree rings to tell how active, how many incoming cosmic rays we had. We can also drill ice cores, which is where we get the beryllium-10, and get a good idea of how many cosmic rays we had coming into the Earth from the beryllium-10 ice cores. Now those cosmic rays are things coming in through the whole galaxy and sailing into the Earth's atmosphere. What's interesting about them is the sun, when it's very active, is kind of keeping them out, pushing them away from the Earth. So they're modulated a little bit by solar activity. So that gives us an indirect record of what the sun was doing via these isotopes that we can trace back for tens of thousands of years through ice cores and through tree rings. So I got this record from beryllium-10 and carbon-14 that goes back quite a ways, and I correlate that with 400 years where we've got sunspots, and then we can take that record back tens, even 100,000 years. So each of these steps gets to be a little more tenuous, but still it gives us a longer duration than what we have without doing them. And that's how you kind of reconstruct what we think the sun has been doing for a long time. We do similar things for what we think temperatures on the Earth have been like for the last hundreds of thousands of years. And then you can start to correlate those. Now there are a lot of causes of climate change, and I don't want to have you thinking the sun is doing everything, far from it. Solar variability is one natural forcing of climate. Volcanoes are another one. There are internal oscillation modes, sort of atmosphere, ocean coupling modes that drive climate, especially regionally. But there can be land cover changes, forestation, urbanization, and there can be other gases, anthropogenic ones often, various gases that we're putting up into the atmosphere that can affect incoming sunlight. So a lot of things can be affecting climate. Break it down into four main ones that people study. El Nino Southern Oscillation, one of these ocean-atmosphere coupling modes. Volcanoes, which can spew particles up into the atmosphere and scatter incoming sunlight. Solar irradiance and anthropogenic forcing. Now, El Nino is kind of a circulation pattern in the Pacific and similar circulation pattern in the air above it. Volcanoes, like I said, can spew aerosols up into the stratosphere, where one of the big effects is cooling. Incoming sunlight's blocked, and if you block that sunlight, it's a huge amount of power you're modulating. Solar irradiance is a combination of faculae and sunspots. And anthropogenic forcing can come from a variety of things, from albedo, snow, greenhouse gases, ozone, carbon, land use. So that's another modulator of what happens to light as it starts to come in. So a simple thing like, is it the sun or is it greenhouse gases that are causing changes? This is another case where it's really easy to start to make mistakes if you're not very careful. Ingram published this interesting paper where taking a record of observed temperatures in red here and solar forcing in green and the greenhouse gas contribution in blue, averaging these things, kind of doing a running mean to smooth things over for 9 years, gives a fit like this, where, and this is a stepwise regression where you take one of these two components, greenhouse gases and solar contribution, and you fit one of them to your temperature record. You say, oh, greenhouse gases fit that pretty well. You remove that, and then you fit the residual to the solar contribution. Now you do exactly the same thing, but instead of using a 9-year running mean, you use an 11-year running mean, and you get a very different answer. Here, it looks like the sun is doing everything. What a lot of this means is you've got to be real careful about exactly what sort of means you're choosing. But another one is you can't stepwise fit individual components and remove them because you're putting in some criteria, some selection process there ahead of time to say which one you think is causing the fit, that is the dominant fit. You need to do all of them at the same time. So we'll take all 4 of our components, El Nino, which can cause short-term increases in temperature. Volcanoes, here's Pinatubo from the early 90s, a short-term decrease. The sun with its 11-year solar cycle, and anthropogenic effects. So those 4 simultaneously fitted via multiple regression to temperatures, shown here in black over the last 30 years. Temperature globally averaged record, and the model of combination of these 4 that fits that record extremely well, explains about 85% of the variations that you see with the multiple regression, and tells you how much sensitivity you have to each of these different components that's driving climate. So let's extend that back further. This is our 30-year record that I just showed. Let's extend that back over 100 years. So we can do that with the irradiances from sunspots. We've got records of volcanoes. We've got records of temperatures that give us an indication of what El Nino's been doing, and records of gases. So this, what it really does is it nicely gets us to times before where anthropogenic effects got to be quite so dominant, to see compare how the fits do in this more recent time era with how they did more historically. So if I take things back a little over 100 years, again, temperatures here, the model fit to them. Not quite as good of a fit going back that far, and the different components that we had contributing to that. A couple of neat things that you find. The fits to the more recent era, the sensitivity of climate to each of those forcing agents is the same for the more recent era as it is for this longer term era. That is, if one of those components changes a little bit, it causes the same change in climate over the long duration versus the short duration. Another interesting thing is the actual sensitivities. Most of the increases that we've seen, this is an increase of a little less than 1 degree Celsius over the last 100 years. Most of that is really from anthropogenic forcing, and most of that from the 1950s onwards. The sun is the next largest driver over that time range, with smaller short-term effects from volcanoes and El Nino. But these natural components now are accounting for less than 15% of the total warming that we're seeing. So it's important, very important to know what they are, because as we're trying to set, governments are going to be trying to set different policies for trying to regulate climate. We need to know how much is stuff like the sun that we simply have absolutely no control over. So even though they're down at the 15% level, they're still large enough drivers that they're things that we need to be monitoring to be able to attribute what's causing climate change that we can control versus what we can't. Now they not only vary with time, we can also take those same 4 components I showed and break them up regionally, because we've got good temperature records regionally. So here's regional effects across the Earth from the solar cycle itself. And this is over the last 50 years, I believe, where, I'm sorry, this is merely over this last solar cycle. Warmer areas that this last solar cycle caused in the northern part of Europe and northern Asia. The effects of the Super El Nino in 1998. Big warm region here in the Pacific, warmer over the northern Americas. Pinatubo caused a lot of cooling over the northern Americas, bit of cooling through Europe and Asia here. And anthropogenic effects really seem to mess up, especially Europe and northern Asia. So we can break up effects and how much is attributed to each of the different causes by region this way. What's going to be happening next? Here's our record that I showed for the last 30 years of temperatures, and here are the contributors to that. A couple that are the most predictable are probably the anthropogenic influences, just continuing them on, and the solar radiance 11-year cycle continuing. Regionally, what that's going to mean is we've been lucky the last few years. While anthropogenic effects have been increasing, the sun has been decreasing these last few years as we've been coming out of solar maximum. And that's meant temperatures have been pretty stable these last few years. That's likely to be changing now as we're heading up the next solar maximum, and the sun and anthropogenic effects are going to be combining. So that should peak around 2014, and then things will stabilize for a while. So that's what's shown here. This is 2014, this is 2019. And they're pretty similar. It's going to be a little bit warmer. This is compared to the 1950s. A little bit warmer in, again, Europe, Northern Asia, Northern America, but pretty similar between these two, and that's because things really aren't changing much there. But now let's start to throw in some other random effects, things that we can't predict so well. El Nino. Let's put an El Nino in here at 2014. Or, I'm sorry, I've got this backwards. Let's put a volcano in there and decrease things. Let's have El Nino peak a couple of years later here in 2019. So here's what El Nino will do. It's going to warm things up. Here's what the combined effects will do. And this one is 2014, so that's mostly driven by this volcano. It'll again cool things in Northern America. Won't have much of an effect here in Europe. But then you throw in the El Nino a couple of years later, and now things really get a lot warmer in Northern America, Northern Europe. Europe's kind of had it in all these cases. They're just getting warm, period. But you can try to break up, given various inputs, how is that going to affect us? How is it going to affect the whole climate? How is it going to affect different regions? So we're starting to get some good understanding of that. Other things that are going to be helping to understand climate change are more measurements of the outgoing radiation. So we've got pretty good measurements that we're continuing of the incoming radiation, but trying to improve the outgoing. We had good shortwave measurements, that is, measurements of the reflected sunlight with spatial information. We could start to tell a lot more about what clouds are doing, how we're changing land use with deforestation or urbanization, what things are changing in the atmosphere with aerosols, how snow and ice cover is affecting things. If we have good measurements of the infrared, we can determine temperature profiles in the Earth's atmosphere and see how that's changing with time. We can directly be measuring greenhouse gas emissions and their thermal infrared signatures. So these are improved measurements that we'd like to be able to start getting these long-term records that we need to understand climate on, to kind of complement the good incoming measurements that we have. We also are starting to get good spectral irradiance measurements. Now the sun doesn't put out all of its energy at one wavelength. It puts it out across a range of wavelengths, and this in blue is the spectral irradiance coming from the sun. That's at the top of the Earth's atmosphere. A lot of that doesn't make it through our atmosphere. Our ozone absorbs pretty much everything below 300 nanometers here, so this is all gone. There are water vapor bands, carbon dioxide bands, where that light just doesn't make it through the atmosphere. It goes directly into heating different layers of the Earth's atmosphere here. So by understanding how those spectral irradiances from the sun are changing, and understanding what effects they have in the Earth's atmosphere will help us better understand how the whole physical processes are working that can be driving climate. So let me wrap things up here, and things I've said are that natural effects, the sun, volcanoes, El Ninos, are occurring simultaneously with the greenhouse gases. They have a smaller effect than the greenhouse gases do, than the anthropogenic effects do, but there's still things that need to be understood to be able to understand climate. We do have a lot of regional variations on all of these influences. That is, it's not affecting things globally. You can go outside and say, oh, it's hot today, that's from global warming. Well, it can vary region by region pretty easily. The natural changes are occurring in sync. with the anthropogenic ones. So like I showed, sun can be, it's been pretty stable or actually going down the last few years. The temperatures have been pretty stable because it's been counteracting some of the anthropogenic effects, and that's going to be varying, getting a bit warmer the next 5 years and then stabilizing the 5 years after that. And what's really important in all of these measurements, whether it's the sun, whether it's volcanoes, whether it's temperatures of the earth, are good, stable, accurate measurements that we're continuing to get. So that's progress on a bit of climate and a fair amount of the sun and how it's affecting our climate. Thanks a bunch for your attention.